Okay. I'm good. Yeah, give me just a second.
Sure.
Pull crap out of my pockets. Jacket's on. Ooh, and the mic's on.
Hi, we have Ned Jackson again here. Ned Lovely Jackson on stage, and he's going to talk to us about machine learning. Please welcome him.
Thank you. Yeah, no worries. Hi, everyone. How y'all doing? So my name of my talk is Enough Machine Learning to Make Hacker News Readable Again. Yes, that's a little snarky. I'm sorry. So what I want to talk about, sort of the focus of this, I should introduce myself too, shouldn't I? And plug in my pointer. All right, so this is me. Oh, by the way, the slides are up on my website, njl.us. I'm NedJL on the Twitters things. You can email at me, njl@njl.us, to, I don't know, ask me questions or yell at me or whatever. So what I'm trying to do here is a simple, achievable project, something that is machine learning related, but I think all of us are capable of, which is a personalized filter for Hacker News. Taking Hacker News and sorting the articles into what I'm going to call Dreck and not Dreck. And then you read the not Dreck, and you feel much better about the world in general. So the whole point of my talk is I can machine learn and you can too. Machine learning has this crazy name, it feels like artificial intelligence, the machine is learning, man. And that's a lot of intimidation. There is a lot of science involved, there's a lot of terminology. You're gonna spend a lot of time Googling, you're gonna spend a lot of time reading Wikipedia articles and survey overviews of stuff. But the essence of machine learning is actually starting to approach engineering. It's starting to approach tools you can use. Machine learning is just applying statistics to big piles of data. That's really all it is. So we've gave it this wonderful name. But when you get down to it, you're building statistical models of a bunch of input data, and you're using it to understand that data better, or to make predictions, or to sort of go further with the data. So yeah, there's terminology, but I'm gonna give you a bunch of it and then try to set you loose. So here's sort of the workflow when you're doing machine learning. You have to get the data, which is usually not as easy as you think. You need to engineer the data, which means you need to take this messy real-world stuff that you scraped off the web or got out of some database and turn it into nice little Numpy arrays with well-formed values. And then you need to train and tune the model. This is the science part, that training and tuning the model. But other people have written libraries. You can just use their libraries. It's great. And then applying the model to new data, once again, you just use the libraries. If you talk to folks who do this for a living, who have doctorates, who spend a lot of time working in machine learning, they spend all their time getting the data and engineering the data. They burn a lot of CPU cycles, but not a lot of time training and tuning models. And then, just applying it is very straightforward. So I'm going to be talking mostly about scikit-learn. The documentation for scikit-learn is fantastic. A couple pip installs away from having a fully functioning, awesome machine learning library sitting on your machine. The hardest part is installing SciPy. So you've got a tutorial, user guides, API docs, and this flowchart. This flowchart is one of the coolest things ever. So the hard part with machine learning is there's too much terminology. There are too many things you can do. There are too many options. People will say, oh, you support vector machines for everything, and they're probably right. But who knows, maybe you're trying to do something else. So what this does, this chart gives you some steps you can go through to figure out what you want to start Googling. All right? It's really that straightforward. You say, oh, I've got less than 50 samples. Oh, never mind. Right? And so you kind of step your way through this flowchart, try to figure out what you're trying to do with your data, and you can start figuring out what parts of scikit-learn do you need to research more. What do you need to find a couple papers on? There's lots of good papers that kind of give you an overview of the field without bogging you down too much. And when you don't understand the math, go blah, 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 and keep reading. That's my advice. So something that we hear a lot about in machine learning, and I think it's worth talking about and bringing up and just making people aware of, is the concept of supervised versus unsupervised. So supervised learning is when you have input data and then there's some output value. So for me, the input data was a bunch of stuff I scraped off of Hacker News and sites that link to Hacker News. That was the input data. And then the output was, is this crap or not, right? So a Boolean value, true or false, true, something I want to read, false, something I wish didn't exist, right? And so that's classification, that's supervised learning, where you go and you have a bunch of labels and output values, and you try to turn input data into those labels or output values. That's supervised learning. Unsupervised learning is more about understanding your data. That would be, I have, thousands of Hacker News articles. Can I visualize them somehow? Can I group them by subjects? And I don't know how many subjects there are, but can I find subjects and group them? So that's kind of unsupervised, sort of trying to understand the data a little bit better. A lot of power to it, a lot of interesting bits there, but I'm going to set that aside for this talk, and I'm pretty much going to be talking about supervised learning. There are a lot of really accessible books on the topic. Natural language processing with Python and programming collective intelligence, the O'Reilly books, aren't directly dealing with the topic of this talk, but they do a really good job of getting you thinking about dealing with big piles of text as data, which is a kind of like a little bit of a thing to stretch your mind to say, you know what, it's text, but I can turn it into numbers, and how do I go about turning it into numbers? The books from PACT, Building Machine Learning Systems with Python and Learning Scikit-learn, are both really good books that step you through step by step, but they tend to kind of walk you through a little bit contrived examples and can hide you from a little bit of the real world. So enough about this. Let's talk about this scikit-learn thing and some patterns, some stuff you're going to see over and over again as you're writing scikit-learn code, and things to look out for and be aware of. So first things first, they love them some parallel arrays. X is the input. So in my case, this is an array of dictionaries with lots of random junk from Hacker News. Y is the value you're trying to get out. So X is the input data. In my case, Y would be a Boolean. True, I want to read it. False, I don't. First thing you want to do with machine learning, and this is one of those hard-won things that the community has finally come to, is you want to set aside what's called a validation set. You're trying to train the computer to notice patterns and to pick up on things on data it has never seen before, right? So it would be trivial to write something which saved all of the input values it saw exactly and then spit out the output values again when it saw those same input values, and it would look like it was perfect. You'd say, hey, look, I put it in, it comes right out. But what you're curious about, what you want to learn about, is new, weird, different, interesting stuff your machine hasn't seen at all. So what the idea of a validation set is you take about 25% of your data and you set it aside totally. You're not allowed to touch it. You're not allowed to look at it. At the very end, you're done with everything, and you use the validation set to figure out if you did a good enough job or not. For me, I marked them all in the database, and then when I was pulling and messing with the data, my validation set didn't show up at all. And then finally, at the end, I used the validation set to figure out how good my results were. So how do you work? What do? You're going to build pipelines, so sequences of things that operate on data, and you're going to optimize parameters. You're going to be tweaking how these things are operating on the data. Pipeline, just a sequence of operations. That's all it is. They are this amazing, wonderful thing that allows you to put together a bunch of potentially really complex steps and then optimize this entire series of complex steps to get the best possible results. So what I have right here, I'm going to get over here so I can highlight some code. I'm just importing the pipeline. I'm getting this text package and a linear support vector classifier. So I create the pipeline. I just give each one of them a name. And basically, this will take input blobs of text and turn them into nice numerical NumPy arrays. And this will attempt to learn from that input text. This is very straightforward. And that's an almost complete, reasonable way, first step, to understand some text and to make some predictions about text. That's really all you need. But there's these things called hyperparameters. So there are amazing amounts of wonderful, tweakable little bits of math going on inside all of these gigantic statistical methods. And if you look, you're like, oh, there's this thing called C, and I want to set it to some power of 2, and whatever. You Google that. You figure it out. You get some vague idea of what's going on. And then you use these things called, well, they got a couple different kinds of ways to do this, but the grid search is amazing. So you basically say, there are, I don't know, 4 different values for C that seem reasonable. There's 2 different values for the loss function. I want to try 2 different values for the n-gram thing. And then the grid search, I set the number of jobs to -1, which means use all my CPUs. I put verbose equals 2, which means print a lot of stuff to the output so that I feel like things are happening. And then I look at htop, and all of my CPUs are pegged red. The fans go on. It just crunches. I actually had one that took 4 hours because I was doing multiple pipelines in parallel and just testing them all out and trying to find the best one. So you just try out all these possible combinations, and it finds out which one is best at predicting your data for you. It does cross-validation, all these other things for you behind the scenes, but you just try a bunch of values, and it tries all the values, it tries all the combinations, and will spit out an object at the end that is the most effective and efficient and accurate trained model. Very straightforward. So that fit function is something you're going to see a lot of. There are 3 functions in particular that are interesting. Transform and fit are both ones you might have to write yourself, and predict is where the awesome statistics people have done the magic for you. That's where the science is in predicts and fits. So this is a transform. The hashing vectorizer, we saw that a little bit earlier, to turn blobs of text into nice little arrays. So all this one does, I threw in 2 parts of import this, and it turns it into a sparse matrix of floats with 10 stored elements. So it just takes this text, this array of text, and it actually, for each column is a word, not precisely, but close enough. Each column is a word, each row is some input text, and it will set those values based on this input text. Really, really handy way to turn text into something you can operate on as if it was numbers. The next step is fit. So this is where the magic happens. I think that's the line. So right in here you say, hey, here's a bunch of input data, and here's what the results should be for that. Right, results should be. That's what the output data should be, is this y. It matches up the x and the y. It does lots of math and statistics, and it figures out what the value, it figures out what it needs to store internally in order to be able to make predictions in the future. Predictions in the future is just this predict thing. You pass an array of things to make predictions on, it spits out an array of guesses, basically. Very straightforward. So that's kind of it. Like, that's the real essence of this. There's lots of engineering, though. The real world, messy, scary. You got to get the data, right? How do you get the data? Request an LXML. So I've got something that scrapes the front 2 pages of Hacker News every 4 or 5 minutes, parse it with LXML, I pull out the links, I crawl the links if I haven't seen them before, and I just basically go through and try to grab all of the data possible that I can from Hacker News. So I have this raw data, but what I need to know is I need to know what's good and what's not good. So I wrote myself a web app to classify Dreck and Non-Dreck. You can't see the big red buttons for bad. They got cut off on the slide. And so over the course of about 6 weeks, I think, I classified 5,000 articles and found about 20% of them were things I was willing to read. It was pretty epic for a while there. I came up with lots of tricks to make this faster, so I controlled F for coin, or NSA, or San Francisco, or a bunch of other things, and just try to get rid of world news and business hacks, and I don't even know, stuff I just don't want to read. And so I would, and this is all my opinion. So anyway, I go through and I click bad, 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 bad. This bring the pain button would show me site after site in an iframe with big buttons at the top for good and bad. So there was a period there where I read everything that made the front 2 pages of Hacker News, almost. So yeah, this was the hard part, right? This was actually the hardest, most involved part in the entire thing, was getting this data that I could then feed into my models. So what data did I have? I had the title that it was submitted with. I had a title if it changed. I had the URL, who submitted it, what was there, what its max rank was, how many votes it got, how many comments, what time of day, and most importantly, and most painfully arrived at, whether I found it to be Dreck or not. So we need to turn this messy data into normalized, happy, healthy, fun NumPy arrays. There's a lot of techniques for turning words into numbers, and I kind of want to give a brief overview of some of them so that you've seen them, and once again, you know what to Google. First up, bag of words. So we have the phrase, time flies like an arrow, fruit flies like bananas. And this is an incredibly grammatically correct, grammatically complicated and deep phrase, right? Like flies is a verb in one, and one's I don't know, that is simile. This is hard for a human being to fully parse, right? So forget grammar. Who needs it? We're going to treat these words as if they were just a bag of words. And we're going to say, oh, flies like time and arrow fruit bananas. Good, they're all in there. Maybe some techniques you count them, some it's Boolean, you say whether the word is there or not. And also implicitly, this doesn't mention Bitcoin. So Bitcoin is 0. So we just kind of count up what's there, treat it like it's a bag of words, and just totally ignore this grammar stuff because grammar is hard. So if you want a hint of the grammar, though, there's this thing called n-grams, and people are always talking about n-grams, and unigrams, and bigrams, and trigrams, and I don't know would it be quadgrams? I don't know. People just say 4 grams. So you just get chunks of words, and you think of these chunks of words as if they were themselves words. So instead of time flies being 2 words, you think of it as time flies, and you think of flies like, and you look at just pairs of words or groups of 3 or 4, however much input data you have and how much memory you're willing to burn. And you just kind of start building this higher level understanding of it that includes just that little hint of the grammar. There's also this concept called normalization. So you sometimes hear stemming and lemmatization, and stemming is generally a hack, and lemmatization means looking it up in a dictionary. This is a really interesting thing. So there's this thing called the snowball stemmer in nltk, which is the natural language toolkit, and has lots of fun things to play with text in it. And you can grab this stemmer and feed it just English language text, and it tries to normalize it. So does it really matter if you say flies or flied or flying or any one of the other couple different parts of speech? It doesn't really matter. They're all kind of the same thing. So when he liked to fly upon early flight. So it just normalizes the words so that it kind of hides a little bit of tenses or plural versus singular. I think it does a great job. And finally, there's this concept called stop words. Oh, not the final one. There's this concept called stop words. And the idea with stop words is there are words which are just useless. They don't give you any information about what's actually going on. If you know that a article that's linked to from Hacker News uses the word the, that doesn't give you any additional information, right? Who cares? All right, it's sort of the fluff that we use in normal English grammar to glue stuff together. There's a set of stop words for English that are included in scikit-learn, and you can just set an option on a bunch of different things to ignore stop words, which can be, a pretty big boost. This is the last thing here. Term frequency, inverse document frequency. So the idea is if you have a word like Bitcoin, and Bitcoin shows up 12 times in this article, whereas on average it only shows up 1 in every 4 articles. This article is clearly very strongly about Bitcoin. It has much more Bitcoin in it than any other article. So let's give the word Bitcoin a little bit of a boost. And let's give the word Bitcoin a little bit of a boost here to kind of, get rid of it. So other stuff here about engineering features. So this is some code I've actually used in my attempts here. So we can pull out relevant text. There's something called readability. And readability LXML is a Python reimplementation of this browser plugin that tries to get rid of all of the junk around the outside of a web page. So recommended links, a menu at the top, ads, all sorts of other stuff that don't directly relate to the main content of the article. It tries to pull them all out with heuristics. And so with readability XML, I take it, I grab that summary, I parse the thing with LXML again, I try to pull out all the text, and then I return the text. So I'm cleaning out all of the HTML tags, I'm cleaning out everything. I'm trying to get just to what is the relevant, actual, real text for this particular HTML page, right? You can also roll your own features. So I had a theory that I liked long-form content. So what this does is, right here in the transform function, it takes an array of text, and it just counts how long each one is and returns that back as a nice 2-dimensional array. And so you feed it text, and you get back out numbers between, 0 and probably tens of thousands. All of these things want the numbers to be centered on 0 and usually standard deviation to either side of 1 to -1. And this standard scalar thing, which is out of the box, takes these random crazy length numbers and centers them on 0 and makes them a nice little even distribution around 0. So I could then have this additional feature that I created from scratch where I kind of inferred something from that source material that wasn't immediately obvious in it. Length. You can also combine features with this thing called feature union. And basically what this does is this takes two Numpy arrays and kind of concatenates them and sticks them right next to each other so that you can feed in multiple signals and stick them together with this feature union. And you also notice I stuck this length pipeline in as if it were yet another thing. So I have like pipelines inside pipelines inside pipelines to sort of massage together different features that then get exposed all the way up. But my data starts as dictionaries. So I'm just pulling this out of a Mongo database because I'm lazy. And this little thing here is a transformer that will pull values out of a dictionary and return those values. So the way I use this is I get this idea that maybe host names are relevant, right? There are places that seem to post good content, and there's places that post awful content, and that should be a signal that should go into this machine learning bit, right? So what I do is I use URL parse to pull out the host name for a URL, and then I just return that. And then I build a pipeline. Once again, I build a pipeline. So I feed this in the raw Mongo results from my database. It extracts the URL from that and turns it into an array of strings. I then extract the host name from that URL, and I pass it through this dict vectorizer thing, which then turns it into a nice numerical NumPy array, which is pretty much always the goal, is to turn it into this nice little NumPy array. So what does the actual application look like? How do you actually use this stuff to do new predictions? You do this. Sorry, Alex. Anyway, save your input data so you can recreate it later. I know of production systems which cannot be upgraded on penalty of death because there's some pickle from like 7 years ago that we can't recreate, and like, don't touch it, right? So anyway, keep your source data so you can recreate it. But you just take that thing and you pickle it. Mine is, I think it's like gzipped. The pickle that does the predictions is like 5 megs, and I've got an Ansible script that pulls it down from S3 and throws it in the right place. Then you just pass in the input data in the same format that it got the input data when you were training it, and it magically works. So I built this thing, and there's a bunch of different colors, most of them having to do with what data I can grab. But red basically means stuff it thinks I shouldn't read, and green is stuff I think it should read. And I put it up at hn.njl.us, and I, like, this morning went, oh boy, I probably better turn caching on for that. So hopefully I did that right. And if you have all this data, right, so you can build this app to sort stuff, but if you have the data, you can do lots of other things. So I mentioned unsupervised learning. Can you look at it and figure out, are there other interesting things I can do here? Are there other, can I cluster it, like I said? Can I find clusters? Maybe you could predict article scores, which would then be really interesting combined with something that watched an RSS feed and maybe auto-submitted. I'm just saying. And the real point of my talk, the thing that I really want to stress, is that machine learning is becoming engineering. This is starting to move out of the range of science where nobody really understands what it does, and you have to read 1 million articles and get a doctorate in this stuff in order to be able to actually apply it to the real world. There are libraries out there that you can use that you can start to understand the properties of. You know, 20 years ago, if you wanted to use a red-black tree, you pretty much had to write it yourself, right? And now we just accept that these fancy things are in libraries. And I think machine learning is going the same way. These are going to be awesome statistical techniques you're going to need to know a lot about the characteristics of, but they're going to be in libraries. They are in libraries, and you can just go use them. So go use them and do interesting things. Thank you. She thanked me for the talk and said we have how long for Q&A? 4 minutes. 4 minutes for Q&A. Do we have any questions? Do we don't have the microphone work. Oh, go ahead. I saw you. Go, talk loud so I can hear you.
When you were gathering data, did you look at search engines, the Algolia stuff?
When I was gathering data, did I look at a search engine?
They rolled out a new search engine that has its own API.
Oh yeah, no, that was older. I did this. I think I did this a couple months before the new search engine. Yeah, so I didn't look at that. You know, frankly, I just need to grab 2 essentially static web pages every 5 minutes. I wasn't really interested in doing in-depth mining of the data. There was enough scary dangerousness in crawling random URLs off of Hacker News and putting them in a database to keep me occupied. Any other questions? Yes, over there.
Could you come up to the mic actually? Or?
Yeah. If we could try to get in line for the mic. Is it working now?
Yeah.
Awesome.
No, it is.
I feel like I should just have you shout your question rather than get in line. So he's wondering about my accuracy with the features I picked. I found the fancier I got, the worse my accuracy got. It's around 90% accurate, and all of the failures, except for one, because I looked at each one because I was like, what's going on? So it's 90% accurate, which I'm proud of, because anybody can get 80%. But it's 90% accurate, and all of the failures are things it thinks I shouldn't read that I marked as I would read. And I went back and looked at them, and they were usually things where I said, oh, I would like to read the first article about the NSA. And then the rest of them, I was like, no, I'm done now. So a lot of my failures were things that I had marked as readable and then changed my mind. Any other questions? We do have a mic we should probably be lining up for. Do we want, go ahead. Somebody back there. Yeah, so basically you do something called cross-fold validation, where you hold out a portion of your data as if it's cross-validation, and you train the other 80%, and then you see how good it is at predicting the 20%. And so you try a bunch of different methods, and I actually built this thing that put like many pipelines in parallel, and then optimized every one of these pipelines, and then picked the best pipeline, and then spit out what that was for me, and then retrained the data so that my pickle was only 25 megabytes raw instead of like 500 megabytes raw. So yeah, you just try out all the options. Like there's all these switches, and you just flip all the switches, and you have the computer flip all the switches for you. And next thing you know, your laptop is very, very hot, and you have something that can predict if Hacker News articles are crap or not. It's amazing. Yes, question?
So can you train as you use it?
Yeah, this whole thing about feedback loops and taking a model and updating the model, there's lots of complicated stuff there that I'm happy to say is sort of starts being out of my realm of real understanding. But I do have some stuff in place where I go through every once in a while, and I will flag a bunch of articles as this one is bad, this one is good, and I will use the fact that it's already been sorted for me to kind of like help me go through them faster. There are techniques for like, updating your model and stuff, but frankly, I'm scared of them. Yes?
You said that you needed about 5,000 articles?
Yep.
Like, what would be the minimum number actually to be able to have anything?
So I did 5,000 articles. What would be the minimum number of articles to be able to do this sort of thing? That's a good question. If you look at the nice little flow chart, it says, oh, do you have at least 50 things? Okay, then you can start doing stuff. But the real sort of weird thing that the way this works is you want your number of samples. So you want kind of the number of rows to be much more than the number of columns. I think we're done. You want the number of rows to be more than the number of columns. And so if you're going to be feeding in text, which by the nature of having all these different words is going to have in many different columns, you kind of need to have a lot of rows, right? So 5,000 might not even be enough. But then again, who knows? Maybe 1,000 would work. Anybody else? All right. Thank you very much, everyone. I really appreciate it.